Swayam Prabha. Digital India. Educated India.
Good morning. In this class, I will be solving some 3 problems related to drying operation. The problem sheet is uploaded in Moodle. You can go ahead and solve by yourself, but I will also be solving in this class. So the first problem is very simple. It goes like this. So a batch of the solid for which the figure below is a drying curve is to be dried. So for this particular solid, the drying rate curve is already given. We know that, so you can see that in the x-axis we have moisture in the units of kilogram per by kg dry solid. In the y-axis we have the rate of drying in terms of kg water evaporated per meter square per second, but also note that there is a factor of 10 power 3. Okay, so this y-axis has to be multiplied by 10 power minus 3. Okay, and so those are the units, and you can see that there is some. So there is a period of constant drying rate. There is a falling rate, linearly falling, and then there is something little different from linearity. So there are 2 falling rate regimes. Okay, so we know about the drying rate curve for this solid, and we wish to dry from 25% to 6% moisture under conditions identical to those for which this figure is applied. That means whichever drying condition is used to get this figure, the same drying condition is to be used for this other the actual batch drying. So the initial weight of the wet solid is 160 kilogram and the drying surface is 1 meter square per 40 kg of dry weight. So instead of giving the dry surface area in meter square, it is given in terms of so much area per 40 kilogram of dry weight, and then we need to determine the time for drying. One of the important things we have to be very careful in drying problem is the basis is whether with respect to the dry solid or wet solid. Okay, with regard to moisture, with regard to area, you have to be always careful with whether it is per unit of dry weight and whether it is wet solid. So these are all very important things to remember. So first what we do is that the moisture content, the initial and final is 25% and 6%, but these are all given in wet basis. Okay, moisture content is based on wet basis, so we have to convert that into, if it is not mentioned, it is always a wet basis. The default is wet basis. This is something I indicated in the beginning when I introduced the terminology. Okay, if not mentioned, it is a wet basis. So okay, so the strategy is the following. First, we have to find what is the moisture based on the dry solid by percentage from 25 to 6%, and then we have to find out here whether this range of moisture from initial to final, whether it falls within a constant period or maybe extends beyond that constant period and also falls in the falling rate period. So that range we have to see. For that, first let us look at the data given. X1 is 0.25. From here we obtain the moisture content based on the dry weight basis. So that is 0.25 by 1 minus 0.25. So this is 0.333 kg water over kg of dry solid. X2 is 0.06 by 1 minus 0.06. This comes out to be 0.0638. So that means in this figure we have to identify where 0.33 is. So 0.33 would be somewhere. So this is 0.35. So I think 0.33 is somewhere here. Okay. So that's somewhere here. Okay. So here is our X1. X2 is 0.0638. So this point is 0.05. So 0.06 would be somewhere here. Okay, so we say this is x2. So clearly it involves the constant drying rate period, and then there is a linear falling rate, and then there is a non-linear falling rate. So it kind of encompasses all the three parts of the drying curve. So what we will do is, we will first find how much time it is taken to dry from x1 to some critical moisture content using a constant drying rate, and then here I know this is a linear curve. Again, I know how to do this for a falling rate with the linear drying curve from the critical moisture content to xd, which is close to 0.1, and then from 0.1 to the final moisture content x2. We can use graphically, or we can probably even linearize this also a little bit and then calculate. So, we are going to separate the entire calculation into three parts. The first range is the constant drying range, constant drying rate regime. So, here I will say x1 is the initial moisture content, which is 0.33, and then the critical moisture content xc is 0.2. Okay. So, from 0.33 to 0.2, it is the constant drying rate. Same unit for x1 and xc. So, this is the formula we can use for constant drying rate condition. So, here what we need is, we need to find the mass of the solid. This is the dry mass of the solid. Okay, so let us go back and see whether it is given. What is given is wet solid weight. Okay, we want dry solid, but the wet solid is given as 160 kilogram. It's an initial weight, and we know initial moisture also. Okay, this is 25% by wet basis. So, the remaining 70% of 160 is actually dry weight. Okay, so we say that SS is nothing but 160 times 1 minus 0.25. Okay, so this is about 120 kilogram. Next, we need area. This area is the area available for drying. Let us see whether this data is given or not. I think it mentioned that the drying surface is 1 meter square per 40 kilogram of dry weight. The actual solid contains 120 kilogram of dry weight. So, the area should be 3 times this. Okay. So, A is 1 meter square per 40 kilogram, but the dry weight we have is 120 kilogram. So, this basically gives me 3 meter square. So, then we can substitute all the known quantities here. This is 120 kilogram, 3 meter square, x1 is 0.333, xc is 0.2. Now, we need NC, that is the constant drying rate, which we can obtain from the figure here. You can see this NC is 0.3 into 10 power minus 3 kilogram water evaporated per meter square per second. So, this is 0.3 into 10 power minus 3. So, the units are this. So, this is kilogram, this is meter square, this is kg water by kg solid, dry solid, this is kg water over meter square second. And so, here you will see that this number, if you substitute all these things, you will get 17,733 in the units of second. No, so what this means is, the way this means is that this y-axis is multiplied by 1000, then you get these values. Okay, so the actual values are 10 power minus 3 times this. Suppose if I had to put this, so I should be doing something like this. Let's say 0.001. This is 0.0002. Okay, instead I am taking a power of 10 power minus 3 and I am multiplying in this units. Like I said, if it is default is always weight basis. Sometimes it's mentioned, maybe for this this particular problem I think this is not mentioned, but usually it is mentioned. If it's not mentioned, you take it as a weight basis. So if you remember, the moisture content is introduced in a weight basis for the first time. Okay, and then if it is not mentioned, you take it as a weight basis. Okay, so now what we have found is time taken for drying from x1 to xc. The next is to find out the time taken for drying from xc to point D, which corresponds to point 1. So the second region is falling rate a linear regime from xc point 2 to xd, which is point 1. And we can also correspondingly read the value of n1 and n2 at these points. So this is 0.15, this is 0.3. So corresponding to this, we have NC of 0.3 into 10 power minus 3. Corresponding to this, we have ND of 0.15 into 10 power minus 3. We have seen that for linear falling rate drying regime, we can use the formula that we derived before. It's basically the same formula for the constant drying rate, except that this n has to be a log mean difference of the two n values at the two end points. Okay, so we are going to just replace the constant drying rate with the logarithmic mean difference. So theta 2 Oh, you're telling me the final answer 18,000. Okay, okay, yeah, close. Yeah, this is 0.2 to 0.1, right? Yeah, this is 0.2 to 0.1. So some 18,500 seconds you should get for a second. So here we have something like 18,484 second. Here we had about 17,333 seconds, 733 seconds. And next is to look at from point D to the final moisture content x2. So here again, like I said, I have tried to linearize this and then get a simple calculation, but You can also do it graphically, you plot 1 by n versus x and then integrate this out if you want. But since this is not very different from linearity, so I am going to use linearized version of the third regime, falling rate, linearized. So here we have xd as 0.1 and x2 is 0.06464, yeah. So n2, so I think it's roughly about 0.025, I think, yeah. This is roughly about 0.025. This should be -3. Anyway, it's a linearized, so you can you can take whatever value that you have. Okay, so that's fine. So I think I'll just take 0.025 and go ahead, and then if you fit it and if you get a different value, that's fine. Actually, this should be done graphically. So I get this time as 20,660 seconds. So total time theta is theta 1 plus theta 2 plus theta 3. This is 18,484 plus 20,660. So the total time for drying is about 15.8 hours. And one thing you can, something interesting to note here is, if you look at these times, the highest time required is actually the last period, okay, where the moisture content has to go from 0.1 to 0.064, okay. So this change moisture content is very little, but yet it takes so long time. That's because the driving force now has diminished. In the beginning, when you are at the constant drying rate, the driving force for the mass transfer is very large. So even for going from 0.33 to 0.2, okay, the time taken is about 17,000 seconds, and then from 0.1 to 0.2 to 0.1 also something of the same order. But then for this case, going from 0.1 to 0.064, because of the diminishing nature of the driving force, the time taken is much larger. And if you want to go from x2 to x star, okay, now it's be even more harder, okay. So what you need to do is then if you want to go to close to x star or even lesser, you have to probably look at different drying condition, maybe use air of higher temperature or lower humidity to start with, okay. With this air alone, you will see that the time taken to reach moisture content closer to x star here is going to be quite time consuming, okay. So that's the takeaway message from this problem. Any comments or any questions about this? You know how to do these things now. So like I was saying, what you could do for this regime is you can actually plot 1 by n versus x between the range 0.064 to 0.1 and then take area under the curve. That will give you more accurate value for this, but here we have linearized it. So there is going to be some error here. So the problem statement is little lengthy, but it is important in the sense that I was mentioning about the actual solid and then drying test with a sample is all there. So please go through this few minutes. So in this problem, the actual sample that we wish to dry is a little larger. It is about 1.2 meter by 2 meter long board. So to determine the drying characteristics, a smaller sample of 1 feet by 1 feet or 0.3 meter by 0.3 meter sized sample with the edges sealed so that the drying happens only from the two faces. This is suspended from a balance in a laboratory cabinet dryer, and this is exposed to a hot dry air. Initial moisture content was 75%. The sheet lost weight at the constant rate of 10 power minus 4 kg per second until the moisture content fell to 60%. So that means from 70% wet basis to 60% wet basis, the drying rate is constant drying rate, whereupon the drying rate fell. So after 60% the drying rate fell. Now the measurement of the rate of drying were discontinued. Okay, the moment it was seen that the rate is falling, no measurement was done. But after a long period of exposure to this air, it was established that the equilibrium moisture content was 10%. So we don't have any data between the critical moisture content to X star. We know what is the critical moisture content, we know what is the equilibrium moisture content. In between we don't have a data. That falling rate, we don't have that information. And then the dry mass of the sample is 0.9 kilogram. All moisture contents are wet basis. Like I said, sometime it is specifically mentioned. If not mentioned, you consider this a wet basis. We would like to determine the time for drying for the larger sheet, the actual sample. Okay, so now we did a test with the sample. We found what's the drying rate, what's the critical moisture content, what's the equilibrium moisture content with respect to the sample, the small test sample. But the actual question is to find the time for drying the large sheet, the original sheet that we wanted to dry, from 75% to 20%. So we know that from 75% to 60% is going to be a constant drying rate. From 60 to 20 it is going to be a falling rate, but we don't have anything about that given in this problem under these same drying conditions. Okay, so to solve this problem, what we need to assume is that the drying conditions are same for the actual and the test sample. So whatever drying characteristics we obtained for the test sample, we will apply to the large sheets also. Secondly, since we don't know anything about the falling rate data, we will linearly extrapolate between the critical moisture content and the equilibrium moisture content with a straight line. Okay, we know that at the equilibrium moisture content the rate is 0. At the critical moisture content, we know the rate is constant rate. These informations are given to us. Okay, so that's the way we are going to go about it. And another thing is very important here is to make the transition between the test sample and the actual sample. Areas are different, dimensions are different. Okay, so it's very important to kind of look at these things separately. Okay, so it's a good idea to write so I'm going to write two things. One is the test sample and the original sample. Okay, so this is the original larger sheet sample. We want to find drying time for the original sample, and here we have the test sample. The drying characteristics were obtained from test samples. So what information we know here? Do we know the area of the test sample? What would that be? So this is a board, square board of 0.3 by 0.3 meters. Okay, but that is area of the one side, but it dries on both sides. Okay, that's the mention. It's mentioned here that the drying took place from the two large faces only. Okay, edges are not playing any role because those are sealed. So the two large faces are drying surfaces. So the area is 2 times 0.3 times 0.3 meter square. So it is basically 0.18 meter square. So this is the area of the test sample. And mass is also given. Mass is given in terms of dry mass itself. So we can directly get this as 0.9 kg. And then the initial moisture content is based on the dry basis. You get something like 3 kg water over kg dry solid. So this initial moisture content is 73% by wet basis. So I am writing in terms of dry basis. Then the critical moisture content is also converted. So this is something like 1.5 kg water over kg dry solid. And the third data is the equilibrium moisture content, which is 10%. So in the case of dry weight basis, so this is 0.11. Now the drying rate, constant drying rate is given in terms of kilogram per meter square second. So we have to convert this units. Okay, the drying rate here is given in terms of kg per second. We have to divide this by area to get in terms of per unit area and per unit time. So we say that NC is 10 power minus 4 kg per second, and then we divide by the area, and area is 0.18 meter square. So you get something like 5.555 into 10 power minus 4 kg per meter square second. So we can use this constant drying rate from 0.75 to 0.6 for the actual sample. Okay, so here we have the original sample, and from x1 to x1 equal to 3 to xc, which is 1.5. So here the drying is constant, so we say that theta is SS by A, x1 minus xc by NC. So this NC is obtained from the test sample. x1 xc is mentioned. Okay, I mean it's the same, initial moisture content is the same, and the critical moisture content is same for both test sample and original sample assumption. But what about this? Do we know about the area and the mass of the original sample? We only know the area, but we don't know the mass. So what can we do about it? So area is 1.2 by 2, 2 times 1.2 times 2 meter square. But what about the total mass, specific mass? So we know that in the test sample we know the area and the dry mass. So from here you can find specific area, so much meter square per kilogram, and use the same thing for the test sample also. One of the variable is given, total area is given. From here you can find the total mass exactly. Okay, so I'm going to use, so this is 4.8 meter square, and so from here A by SS, this is specific area, is 0.18 by 0.9, which is basically 2 meter square per kg. So this is 0.2 meter square per kg. So we'll keep this same for the original sample also. So since A by SS is 0.2 meter square per kg, so this is going to be A by 0.2 . So you get 24 kilogram. So now we know all the quantities that we need here, so we can substitute. 24 kilogram, area is 4.8 meter square, x1 is 3, x is 1.5 and NC is 5.5.5 into 10 power minus 4. So we get something like 13,500 seconds. Now for the original sample, the actual final moisture content that we want, X2, is 20%. Yeah, it's 20%. Okay, so this is going to be 0.25. So from XC, which is 1.5, to X2, which is 0.25, we will assume linear falling rate, because this is the only thing we can do, because we don't have any information about the falling rate period. So we will use this as an assumption here. So that means pictorially what it means is that I have X here, NC here. So we have, so this is my X1, this is my XC and this is my X2. Okay, so I am not having any initial period and I don't have any equilibrium moisture content is given, I think, okay, somewhere here, but our final moisture content for the original board is 20% by wet basis. In terms of dry basis, it's only 0.25. So now for this range, we will use the assumption that it is linearly falling from XC2 all the way to X star, but the actual moisture content that we want is from XC to X2 only. Okay, so for this I am going to use the formula that we derived before, that theta is SS by A, X2 to XC dx by n, and this n here is expressed in terms of a linear relation. So this n here is the equation that describe the linearity between XC to X star. So NC by XC minus X star is the slope of the line, and X minus X star is the you can find n from n at any x value using this equation. For any x, you can find n from here. So now we can substitute this and then integrate this out, and then I'll give the final answer. This is something you can test this later on. So let me just summarize this here. So what we have done here is we have from x1 to xc the constant drying rate from the test sample we are using, and then for the falling rate from xc to x2 we don't have the information. So we are assuming that from the critical moisture content to the equilibrium moisture content the falling rate is linear. Then I write the expression for the moisture dependent drying rate n as a linear function. This is now substituted here and integrated out. Okay, this formula is something we derived in the one of the previous classes also. From here onwards is a direct substitution, because I know the critical moisture content, I know the equilibrium moisture content, NC is obtained from the test sample, and then x2 is specified. So if you substitute all that, you will get a direct substitution. Okay, and now because of time, the third problem I will not do it in detail, but then I'll just illustrate one issue, and then you can just try this at home. I wanted to include this problem because if you do an unit operation, mass transfer unit operation lab, this is the kind of raw data you will collect. Okay, so it's very important in that sense. How do we reconcile this raw data and then convert into a drying rate? That's the, so it goes like this. A laboratory drying test was made on a 0.1 meter square sample of a fibrous board like material. The sample was suspended from a balance, its edges were sealed, and drying took place from the two large faces like the previous problem. The air had a dry bulb temperature of 65 degrees Celsius, wet bulb temperature of 29 degrees Celsius, and its velocity was 1.5 meter per second past the sample. So these are the drying conditions for the test sample. The following data are weights recorded at various times during the test. So time versus mass. This mass is the total mass of the wet solid. It contains the dry mass plus the moisture content, and you can see that this moisture content drops, I mean the total weight drops. Okay, so it's done in two sections. So up to 4.2 here, and then it continues from here. Okay, and you can see that by the time you go to 14 hours or 16 hours, this final moisture content or the total weight basically remains constant. Okay, so these are raw data. You will actually record this if you were to do an experiment. Okay, so what we want to do is the sample was then dried in an oven at 110 degrees Celsius, and then we do this because we want to find the dry mass. Okay, and this comes out to be something like 3.765 kilogram. Now plot the rate of drying curve n versus x that we need to draw. The second is estimate the time required for drying the same sheets from 20 to 2% moisture wet basis using the air of the same temperature and humidity, but with 50% greater velocity. Assume that the critical moisture content remain unchanged between the two conditions. So here we are doing a test under certain conditions. Okay, but we want to calculate the drying time for another condition where everything was kept constant except one variable, which is the air flow velocity is increased by 50%. Okay, so what we need to do here is then we have to find the constant drying rate from the test sample, and then we get a correlation between how the flux will change with respect to air velocity, and then we scale it accordingly and use a scaled drying rate for this problem. Okay, so let me quickly open an Excel sheet. This is something I'll share with you. You can also do this later. So what I do here is, so this is the actual raw data. Okay, so the first thing I do is I subtract from the mass, I subtract the dry weight, then I get kilogram of water, and then divide this by a dry weight, I get x. So I can get time versus x. Okay, so that would look like this. Okay, so this is the drying curve. You can see the initial is not there, and then you can see it reaches some sort of an equilibrium moisture content. Okay, this is a time versus moisture content, x versus t. Then what I do, I find the time difference between two subsequent points, delta t and delta x, and I get a slope, and I get a slope and then divide the slope with the area to get n. Okay, so between subsequent point I take delta x and delta t, find the slope at that x. So I make a data between x and n. okay, and if I plot that, I basically plot drying rate curve, which should something look like this, okay. So you can see that there is some initial fluctuation, which is not seen in this data, but you can see in the rate data there is some initial fluctuation, but then you can see there is some sort of a constant drying rate, and then clearly there is a falling rate, and the falling rate is not linear necessarily, okay. So to distinguish it, I have drawn a linear line here connecting from equilibrium moisture content here. You see it is little away from the linearity. Now once this data is known, we will read the constant value somewhere here, and then we will also identify the critical moisture content close to be 0.15, and then read the NC value, and then using that NC value you go and say that NC is proportional to air mass velocity to the power, let us say 0.5, okay, rescale it and then get NC. And then for the original sample, I think the what we want to do is, so let us go back to the problem here, 20% to 2%, okay. So 20%, if you convert it into dry moisture content, it will be like 25%. So going back here, from 25% from here to 0.02 somewhere here. So you want to find the drying rate. Again, you can do for the constant drying rate based on the scaled drying rate, and from here onwards you have to do graphically, okay. And here we are making an assumption that this falling rate period is not sensitive to the change in air velocity. We are going to assume that the changing the air velocity only changes the constant drying period, not the falling rate period. How do we justify that? So we are saying that between the test sample and the original sample, I am changing the air velocity. When I change this air velocity, I am only scaling the constant drying rate, and I am not doing anything about the falling rate. I am not changing the equilibrium moisture content, the slope, the equilibrium moisture content, the critical moisture content, nothing is changed with regard to the falling rate. How do we justify this assumption? It is solid control drying, exactly, okay. In the unbound moisture drying, which is the constant drying rate, there the drying is controlled by the gas phase. So if you change the gas phase property, it's going to change, whereas the falling rate is broadly controlled by water diffusion inside the solid. Whatever you do on this gas may not affect so much. It is driven completely by the internal mass transfer within the solid. So we can fairly assume that it's not going to change much when we change the drying condition outside, okay. So that is the assumption that you're going to make. So using that assumption, you can make this calculation. I will share the solution and this Excel sheet for you to practice. Not constant here. There will be so yeah, so it will go up here, but XC remains the same. It won't be there won't be discontinuity because you are not comparing these two. So you have to remake this plot again, okay. You will make the plot again for a, let's say, for the original sample with a new NC, which will be somewhere here, and XC is not changed. From XC to here you have to extrapolate, okay. So we'll stop here.